Welcome dear students. So we are once again here on this YouTube channel, namely Knowledge Entertainment. So we start from where we have left yesterday in the set theory. So first of all we will define now complement of a set. So yesterday we have seen set is normally denoted by capital English alphabets and U is the symbol for the universal set. We know the difference of two sets, that means A difference B, denoted by A minus B. Now U minus A, that means universal set minus A, is denoted by A and superscript C and is called complement of A. This is the set complement of A. If we see diagrammatically, suppose this is your universal set U and here is your set A, then complement of A means everything in universal set which is not in A. So this is your complement of A, the lined portion, that is A complement. Now we move on to one more result, that is called De Morgan's law. De Morgan's law states that there are two laws, De Morgan's laws. Number one, A union B, complement of that is A complement intersected with B complement, and secondly, A intersection B, complement is A complement union B complement. So these two are the De Morgan's laws. Now let us prove one of them. But before proving these laws, we will have to go to the definition of subset of a set. So I will move to the definition of subset and then we will come back to the proof of these De Morgan's laws. So let me define now subset of a set. Subset of a set. Let A be any set. Let A be any set. Then a set B is said to be subset of A if for every x belonging to B we have x belongs to A. That means B is a subset of A if every element of the set B is also a member of A. In that case we will say that B is a subset of A. Diagrammatically, suppose this is your universal set U, here is your set A, then B is a subset of A if B completely lies within A. That means B is something like that. So B is a subset of A and this is the symbol, that is the notation that we read it as B is a subset of A. Or we can also say that A is a superset of B. These two statements are vice versa correct, that if B is a subset of A, then A is called a superset of B. Now let us move on to some example. Let me write a set. I am writing a set A consisting of three members, namely A, B and C. Let us write all the subsets of A. One thing is to be noted that phi, that means empty set, or you can say null set, or you can say void set, is a subset of every set. So when I write all the subsets of A, phi will definitely be there. So phi is the first subset of A because phi is subset of every set. Then you can write the singleton set A. This set is also a subset of A because it contains only one element A and that is also there in capital A. Similarly, the singleton set B is also a subset of A. Singleton set C is also a subset of A. You write two elements in the set A and B. Then this set is also a subset of A because every element of this set is also a member of the set A. Similarly, the set consisting of two elements A and C is also a subset of A. The set consisting of the elements B and C is also a subset of A. And another thing is to be noted that every set is a subset of itself. That means A is a subset of A, so A is also a subset of A. Now, these two subsets, the first one and the last one, phi and the set itself, these are improper subsets of A. Every other subset of A other than phi and A is called a proper subset of A. So how many subsets of A are there? 1, 2, 3, 4, 5, 6, 7 and 8. But how many proper subsets are there? Then 1, 2, 3, 4, 5 and 6. In some of the textbooks, A is also considered to be a proper subset. But actually, phi and the set itself are not proper subsets of the set. One thing is to be noted that if A contains n elements, that means number of elements in A is n. That means I want to write that A has elements x1, x2, x3 and xn. N elements. If the set A consists n elements, then number of subsets of A, number of subsets of A equals 2 raised to the power n. And this 2 power n includes these two improper subsets as well. Now look at here. Here the set A consists of, how many elements are here? Here number of elements in A is 3. And how many subsets of A are there? It must be according to the formula 2 power 3. 2 power 3 means 2 multiplied by 2 multiplied by 2. That means 8. And exactly 8. 1, 2, 3, 4, 5, 6, 7 and 8. 8 subsets of A are there. So it is a formula for you that if A consists n elements, then number of subsets of A is 2 raised to the power n. Another thing, here we have written A and all the subsets of A. The collection of all the subsets of A is also a set because it consists of elements. How many elements? 8, that means 2 raised to power n. And this set, that means the set of all subsets of A is denoted by PA and is called power set of A. Power set of A. Now, number of subsets of A is 2 power n. So, number of members of power set of A is also equal to 2 raised to power n. That means, if number of elements of A is n, then number of elements of power set of A is 2 raised to the power n. If a set A consists of n elements, then its power set must consist of 2 raised to the power n elements. So this is the story of power sets, subsets of a set. Now, another thing, when two sets are said to be equal, suppose A and B are two sets, then A will be equal to B if and only if A is a subset of B and B is also a subset of A. That means every element of A is also a member of B and every element of B is also a member of A. In that case, we will say that the sets A and B are equal. In fact, this is the method to prove the two sets to be equal. If you want two sets to be equal, then what we have to do? We have to prove that each one of them is a subset of the other. Now this theory we will use to prove that De Morgan's laws we were talking earlier of. So first of the De Morgan's laws is A union B complement is equal to A complement intersection B complement. This we want to prove. Now if we want to prove this, that means we will have to prove that this is a subset of this and this is a subset of this. So how to prove that A union B complement is a subset of A complement intersection B complement? We will take one element from here, an arbitrary element from this set, and we will prove that that element also belongs to this set. That means every element of this set is a member of this set, which will prove that this set is a subset of this set. And similarly, we will do the converse part, and that will show that A complement intersection B complement is a subset of A union B complement, and when both the sets will be subsets of each other, they will become equal. So let us start the proof. What I am going to start with, I am taking one arbitrary element from here. Let X be an arbitrary element of the set A union B complement. Now X belongs to A union B complement. And what is A union B complement? A union B complement means everything other than A union B. That means if X is in complement of this set, then X cannot be a member of A union B. So this means X cannot be a member of A union B. Now look at, if X belongs to A, then X belongs to A union B also. If X belongs to B, then X belongs to A union B as well. But X is not in A union B. That means X neither belongs to A nor belongs to B. Because if X belongs to any one of them, then X will be in the union. But X is not in the union. That means X is not in any of these two sets. Now X is not in A. When X is not in A, then it means X is in complement of A. There are two things. Look at this Venn diagram. This is your A, and everything that is outside, this is A complement. If something is there in A, it cannot be in A complement. And if something is not there in A, then where it is? It is in A complement. So X is not in A. So when X is not in A, then it must be in complement of A. And X is not in B, that means X is in complement of B. Now X is an element of A complement and X is an element of B complement. So that means X is a common element of these two elements. And all the common elements of two sets, where they are? They are in their intersection. Because intersection of two sets contain common elements which are present in both the sets. Now X is present in both these sets, in A complement as well as in B complement. So that means X belongs to A complement intersection B complement. We have taken X from this set A union B complement, and what we have seen that X is in this set A complement intersection B complement. And what is X? X was an arbitrary element of this set. That means every element of this set is also a member of this set. And when every element of one set is a member of the other set, then the first set is the subset of the second. So what it proves? It proves that A union B complement is a subset of A complement intersection B complement. Let us take this as result number 1. Now I start again from the other side. What I will do now, I'll take one arbitrary element from here now and will show that the element belongs to this set. So let X be an arbitrary element of A complement intersection B complement. X is an element of intersection of these two sets. When an element belongs to intersection of two sets, that means X is a member of both of these two sets. Because if X does not belong to any one of them, it cannot be in the intersection. But it is in the intersection. So that means X belongs to A complement and X also belongs to B complement. Now, X belongs to A complement, that means X cannot be a member of A. Similarly, X belongs to B complement, that means X cannot be in B. Now, X is neither in A nor in B. So, how X can be in A union B? Because A union B contains those elements which are either in A or in B. But X is neither in A nor in B. So that means X cannot be in A union B. X is not in A union B. If an element is not present in a set, then where it is? It is in its complement. Now X is not in the set A union B. That means where X is in A union B complement. From where we have taken X? We have taken X from A complement intersection B complement. And where X is falling? X is falling in A union B complement. And X was an arbitrary element of this set. That means every element of this set, A complement intersection B complement, is also a member of A union B complement, which directly shows that this set, A complement intersection B complement, is a subset of A union B complement. Let it be 2. Now look at 1 and 2. 1 says that A union B complement is a subset of A complement intersection B complement. 2 says that A complement intersection B complement is a subset of A union B complement. That means these two sets are subsets of each other. And when two sets are subsets of each other, then they are equal. So what follows from 1 and 2? From 1 and 2, we can say that these two sets, A union B complement and A complement intersection B complement, they are equal. On the same lines, the second De Morgan's law can be true. So it is an important law and is used in several places in higher mathematics. So you have to keep it in mind, that is De Morgan's law. Now we discussed some more laws. In the previous lecture, I discussed commutative law, associative law, distributive law, and now I am discussing some more laws, that is absorption law. Absorption law. Absorption law. There are two absorption laws in fact. Number 1, A union with A intersection B is A, and secondly, A intersection with A union B is also equal to A, and these two laws are known as absorption laws. So these are the absorption laws. And next I move on to some important results, and these results are, suppose if we look into the Venn diagram, here this is the set A, suppose this is the set B. Now what is A intersection B? A intersection B is the common portion. This portion, this is your A intersection B. And what is your A union B? This is your A union B. Now, if we talk about number of elements in A union B, A, B and A intersection B, what is going to happen? So, number of elements in A union B. It will straightforward come into our mind that number of elements of A union B should be equal to number of elements of A plus number of elements of B. It will straightforward come into our mind. But look into the diagram, what is happening? This is your number of elements in A, this is your number of elements in B, and the whole portion is the number of elements in A union B. Well, you will add number of elements in A to the number of elements in B. This portion will be coming there twice, because this portion belongs to A as well as B. When we will add number of elements of A to the number of elements of B, this portion will be in the number of elements of A and this portion will also be there in the number of elements of B. So this portion will be counted twice. But in the union of A and B, this portion is only once. That means this portion is added one more time, one extra time, which we will have to subtract. That means what we have to do, minus number of elements in A intersection B. So this is your first formula for counting the number of elements of A union B, A intersection B, number of elements of A or number of elements in B from the given data. So this is a formula for you. Now look at what will happen if A intersection B is 5. That means A and B are disjoint sets. Then the number of elements in A intersection B will be equal to 0. And this formula will take the form number of elements in A union B is equal to number of elements of A plus number of elements of B, because this term is now 0. So if two sets are disjoint, then the number of elements in A union B is simply the sum of the number of elements in the two sets. But not usual, not in general, because in general, number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. This is a simple case because we are having only two sets, namely A and B. Now look at a little bit complicated case when there are three sets. Now this is the case, there is a set A, there is a set B, and there is a third set C also. So look into the portion, this portion. This is A intersection with C. Look into this portion. This is B intersection with C. Look into this portion. This is the portion A intersection with B. And if I talk about the union of the three sets, then these three portions will be added. So the formula will be a little bit complicated now. Now, number of elements of A union B union C will be equal to number of elements in A plus number of elements in B plus number of elements in C minus number of elements in A intersection B minus number of elements in A intersection C minus number of elements in B intersection C plus number of elements in A intersection B intersection C. This will be the formula for counting the number of elements in A union B union C when there are three sets A, B, C intersecting each other. Yeah, if these three sets are disjoint, that means if A intersection B is 5, A intersection C is 5, B intersection C is 5. If this happens, that means A, B and C are mutually disjoint. Every two sets are disjoint to each other. Then this formula will be very simple. this will be A, number of elements in A union B union C is equal to number of elements in A plus number of elements in B plus number of elements in C. So this is the formula when the three sets A, B, C are mutually disjoint. Now come on to another very important formula in such cases. That is, if we will have the three sets, suppose you are asked the number of elements in exactly one set. That means this portion plus this portion plus this portion. We don't want these portions. So that means number of elements in exactly one of the sets. So we are talking of the case when there are three sets A, B and C, and these three sets are intersecting each other, and what we want number of elements in exactly one of the sets. Then number of elements in exactly one of the sets A, B or C, the formula will be number of elements in A plus number of elements in B plus number of elements in C minus 2 times number of elements in A intersection B minus 2 times number of elements in B intersection C minus 2 times number of elements in A intersection C plus 3 times number of elements in A intersection B intersection C. This is the formula if we are asked to find the number of elements in exactly one of the sets. Now we move ahead. If we are asked number of elements in exactly two sets. Exactly two sets means either this portion, I am talking about these portions number 3, 4 and 5. If we are asked to find number of elements in exactly two of the sets, that means number of elements lying in these portions 3, 4 and 5, then the formula will be, first to write number of elements in exactly two of the sets A, B and C, then it will be equal to number of elements in A plus number of elements in B plus number of elements in C minus 3 times number of elements in A intersection B intersection C. This will be the formula if we are asked to find number of elements in exactly two of the sets. And if we are asked number of elements in exactly three sets. Exactly three sets means this portion. I am writing here 6. This is the portion. This portion 6 contains those elements which are exactly in the three sets. That means present in all the three sets. And what is this portion? This is portion which is common to A, B and C, all three. And the number of elements in exactly three of the sets will become, therefore, it will be straightforward number of elements in A intersection B intersection C, because it is a common portion. If we are to find number of elements in at least or at most two sets or in at least one set, then by adding these we can get the further results. Now I am stopping the video here. I will continue from here in the next video, and I will try to finish this chapter in the next video so that 3 lectures will be there in complete theory of sets for +1 CBSE syllabus. So thank you all, and I like if you share these videos, if you like my videos, and if you subscribe this channel for the coming lectures on plus one mathematics. Thank you all.